When designing thermal management for electronics, you often deal with air flowing across a cold, inactive substrate before it ever reaches the component you actually need to cool. From the exact physical edge where the air meets the board, friction takes hold. A velocity boundary layer begins forming immediately, slowing and thickening the air down as it moves downstream. But the thermal boundary layer, the zone where heat transfer occurs, remains at zero until the flow hits the heated section. At that point, the thermal layer begins to grow fresh from the surface. Because this thermal layer starts later, it is significantly thinner than the velocity layer surrounding it. Since thinner boundary layers offer less resistance to heat transfer, the cooling is actually more effective than if the entire plate were heated from the start. We use a mathematical correction factor to account for this localized boost in performance. Let's apply this to a standard textbook scenario, problem 7-42. We are evaluating a 15mm silicon chip mounted flush with a substrate that provides a 15mm unheated starting length. Air flows over the surface at 25 meters per second. Before calculating, we must carefully map the geometry to avoid the most common error, confusing the total distance, x, with the unheated starting length, xi. The leading edge is x equals 0, and our unheated length, xi, is 0.015 meters. Since we measure from the velocity boundary layer's start, our critical x value for the chip's trailing edge is substrate plus chip, 0.030 meters. With our coordinates locked, our next requirement is to determine the flow regime at that exact trailing edge. We cannot select a heat transfer equation until we know if the air is laminar or turbulent. Looking at the calculation here, we use the velocity of 25 meters per second, our total distance of 0.030 meters, and the kinematic viscosity of air. This gives us a Reynolds number of 4.171 times 10 to the fourth. That value is well below the critical transition threshold of 5 times 10 to the fifth. We can confirm the flow over the entire chip remains strictly laminar, allowing us to proceed with the laminar set of equations. This brings us to Kay's and Crawford's local Nusselt number equation for laminar flow over a plate, with an unheated starting length, labeled here as equation 7-27. Notice the standard coefficient of 0.332. However, a detail in the problem forces a modification. The chip dissipates 1.4 watts uniformly. This means we have a constant heat flux condition, not a constant surface temperature. To account for this isoflux condition, we replace the 0.332 coefficient with 0.453. Here is the calculation using our modified formula. Plugging in our thermal conductivity, Reynolds number, Prandtl number, and our precise x and xi values yields a local heat transfer coefficient of 102.3 watts per square meter Kelvin. Now that we have the local convection coefficient and the uniform heat flux, take a moment to pause the video. Try using Newton's law of cooling to find the final surface temperature. We divide the heat flux by our local convection coefficient and add the ambient air temperature, giving a final surface temperature of 80.8 degrees Celsius. Arriving at that correct temperature is only possible by meticulously pairing your physical coordinates along the plate with the exact thermal boundary condition required by the hardware. Let's push this system to its limits to see how the math scales. Suppose we take the same geometry, but blast the cooling air across the surface at 300 meters per second instead of 25. That 12-fold increase in airspeed pushes our Reynolds number well past the 5 times 10 to the fifth threshold. The boundary layer has now transitioned from laminar into the turbulent regime. Returning to our reference equations, we must now use equation 728 for turbulent flow. The structure is similar, but the dependencies have shifted. Notice the exact changes in the exponents. The Reynolds number dependency increases from a power of 0.5 to 0.8, reflecting the highly mixed nature of turbulent flow. Additionally, the penalty imposed by the unheated starting length becomes mathematically harsher, changing to fractions of 9/10 and 1/9. As a final step, you must clarify your end goal. The equations we used so far, 727 and 728, provide the local Nusselt number for one specific point. If your design requires evaluating the total heat dissipated across the entire heated surface, you must use equation 729 or 730 to find the average convection coefficient. Solving external convection problems with unheated starting lengths requires a strict sequential process. You identify your geometry, Calculate the Reynolds number to verify the flow regime, confirm your surface thermal conditions, and finally, decide whether your thermal model needs local point data or a system-wide average.